Okay, time to record the lecture where I'm actually recording this time. It's been a fun day. I am getting significantly better. I do think I will probably be good for Tuesday. Probably like a 75% probability. My goal today is to try to recover as much as I can. Well, that was my goal the whole weekend, and here we are. But yeah. So now I'm just at the tail end of everything. I'm still coughing up stuff. It doesn't hurt to talk anymore. So like the laryngitis kind of effects, assuming I had laryngitis, are gone. But my voice is still hoarse. On its own, that wouldn't have kept me from coming in. But the coughing and I definitely shouldn't at this point in time. So I apologize, but I want to keep you guys from getting sick. Okay, so let's go into the lecture. So what this lecture is going to cover is the tail end of convergence stuff for Fourier, tying everything over into Fourier, which is the more important aspect of our convergence, and then briefly talking about differentiating and integrating Fourier series. Okay, so we'll start by talking about this theorem. So this theorem is something that won't be on the final, but it is kind of useful to kind of get a intuitive feel for these convergent types of convergences. So if f converges in the mean, then it need not converge pointwise or uniformly to f. So the idea is the mean convergence just basically means the average, right? So just intuitively, this is not a mathematical proof, but intuitively, if the average converges, that doesn't mean that it has to converge for every single point, right? And if the average converges, that doesn't mean that the maximum error converges. So to give you an example of this exact scenario, if I let fn of x be the function 1, if x is not equal to 0, and 0 if x is equal to 0, and I compare this to the function f of x, that's just 1. So fn of x is a very boring sequence. It's the same function every time. It looks like 1, other than at 0, I cut out a point and I put it down here, right? So f of x versus fn of x. Well, fn would converge in the mean to f of x because this single point doesn't have any weight, right? So you pick some fixed interval ab, I am going to get this convergence to the mean on that interval to f of x because, well, it's well behaved, right? Well, the single point doesn't do anything. But it's not going to converge pointwise because this point's wrong, and it's not going to converge uniformly because this point's wrong, right? So mean convergence is kind of a weaker convergence. It doesn't imply the other two, right? But it can be implied by some of the other two. Kind of thing. Okay, next. If I converge pointwise, I don't have to converge in the mean, and I don't have to converge uniformly. So the example that I just drew, and I'm erasing now, was one where it didn't converge neither pointwise nor uniformly, but over here we saw an example where it converged pointwise, but did not converge uniformly, right? So we're not guaranteed, like if I have pointwise convergence, I'm not guaranteed uniform. I'm also not guaranteed convergence in the mean. That was the idea of this circle thing, where I do the circle and I do the thing, right? When I built that extension of the square to pointwise converge to the circle, the length of the square didn't converge to the length of the circle, right? So that's kind of the idea here. But if you do converge uniformly, you do converge in the mean and you do converge pointwise, right? So the idea here is that if I converge uniformly, then the maximum error goes to 0. Therefore, the average error and the error at each point also has to go to 0, right? And do notice that this analogy that I've been using with points and average and max isn't exact, because if you try to apply the similar analogy to point 2, you say, well, it converges pointwise, so every point goes to 0. Therefore, the average has to go to 0, right? It's not necessarily true, because you can get the mathematical details strongly matter, hence why the proof is beyond the scope of this class, right? But over here, that analogy is kind of a way to think about it, but it's not actually valid for a proof, right? Proof for this would be like a real analysis type course, where you would actually, well, what you do is you look at the different metrics for convergence, and you try to bound give one by something that goes to 0, given some facts about some other bounds you have from the other convergence. So here I know the integral goes to 0, given that the integral goes to 0. Well, this one's just a counterexample. So here I know that the supremum goes to 0. Given that that goes to 0, I want to get bounds for every point, and I want to get bounds for the integral, right? This one, yeah, that's the idea. Okay, so applicability. So thus far we've been talking about sequences of functions, right? But when I write an infinite sum, that infinite sum is literally this limit of this finite sum. This is a limit of a sequence of functions. So everything we've been doing directly applies to our work with Fourier series. Okay, before we talk about convergence, we need to re-talk about what piecewise C1 is. So here's a formal definition of it. I gave a formal definition previously when we used this for some of the existence criteria for solutions to second order DEs. But just remember the definition, kind of familiarize with it. The intuitive idea is that my function's piecewise C1 if it's piecewise defined, so it's defined on, say, a bunch of intervals, right? And within these intervals, it's sufficiently well defined, right? So the function exists, it does some stuff, and the stuff that it does doesn't keep my function from becoming unbounded, right? Oops, let's not do that. And the derivative stays bounded. So on each of these intervals, the derivative exists. If I look at it, sure. The derivative is continuous. If I look at it, sure. And the derivative is bounded, right? So we gave some examples of this in previous lectures. Go back, review them if you don't recall the definition. But it's going to be used strongly for Fourier series stuff. So you definitely need it. But yeah, that's the idea. Okay, periodic extensions. So previously we talked about tau periodic functions. This is a similar idea, but slightly different. So the periodic extension of a function f, defined on a finite interval, will be a b minus a periodic function called fp, such that a bunch of stuff, right? So here's the idea. We have a function on an interval. I'm going to extend this function to be on the whole real line, and it's going to be extended to be the tau periodic version, right? So we've talked about what a tau periodic function is. Now we're just extending to get one. And I have some very particular criteria here that are carefully chosen so that it behaves well with Fourier. So if f is continuous, then the periodic extension agrees with f. If f is not continuous, then f of p is the average of the one-sided limits. And at the points a and b, the endpoint is defined to be the average there as well. So the idea is, if I were to take f and try to extend it to the whole real number line in a periodic way, the stuff at b, like f of b, is going to interact with f of a, and I have to pick which value to pick there. This averaging value is treating it as if it were to be discontinuous, and if it were to be continuous, then the average will be f of a. It'll also be f of b. So in that case, it still agrees with the continuous branch. Right? Okay, so it turns out that this key definition, this is what a Fourier series converges to. Fourier series will always converge to the periodic extension. So yeah, I would ask for questions, but again, video. Okay, so draw the periodic extension of this. So what I'm going to first do is draw the function f itself. So here, negative pi to 0, minus pi, 0, pi. Here, I'm at minus 1 down here. I'm at positive 1 up here. And make that a bit longer. There we go. So here, from negative pi to 0, open circle. Open circle. Here it's closed circle. I'm going to draw open to start with, and then I'm going to close it for reasons. There we go. Okay. So that's what f currently looks like. I need to build a periodic extension. So between negative pi and pi, where f is continuous, I leave it alone. Okay. Where f is discontinuous, I need to make it the average. So it's discontinuous at the point 0. The average to negative 1 and 1 is 0, so I remove the dot and I put the dot here. Also at the edge points, I replace the function value with the average. So here, I define the average, there I define the average. This is what the periodic extension looks like, but it's a periodic extension, so I should probably show a couple periods of it. So here, it copies this over, up here, 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 here. And it goes the other way too. Here, oops. Yeah, this is here. Then I go down here, then I do this kind of thing, right? That's the periodic extension of f. If I were to compute the Fourier series of this function, it would converge pointwise to this. It would not converge uniformly because it can't. Fourier series can't converge uniformly to a discontinuous limit. Yeah, so we're going to have a theorem that will tie all these things together, but that's the idea, right? So this is why we want the different types of convergences, because depending on what the function is, you're going to have different convergences that will lead to different physical behaviors. So yeah. Okay, let's talk about the convergences. So this is our big theorem. If you don't know anything about the convergence stuff that we've done throughout the entirety of like the last lecture and a half, 2 lectures, this is the theorem to know. This is the theorem you're going to be tested on. This is the theorem you're expected to know. All the stuff we've done with the different convergences, with different functions and that kind of thing, has all led up to trying to give you some intuition about what the words are here, some exposure to the topics, so that this makes a bit of sense. Okay? That was kind of the grand design of introducing the convergence stuff. We could have literally introduced convergence definitions, jumped straight to this, but no one would be able to follow that. Okay, but that's the idea. Let's talk about the theorem. If fp is the periodic extension of f, so I give you f on this interval. Given that, I do the things we just did to build fp. Then the Fourier series of f converges to the mean to f and also fp on any finite subinterval of this, right? So in order to converge to f, it has to be defined at the point where f is defined, hence why I limit here. If I want to talk about fp, it'll work on any finite subinterval anywhere, right? The idea of this is the difference between f and fp is just a finite number of points where things are kind of wrong, or where f is discontinuous. There are functions that have infinite discontinuity, so you can get some weirdness there, right? But given the functions that you generally see, you can, in engineering, you can think about f as being mostly nice, right? Nevertheless, if f converges to the mean to f, and fp only differs from f at a discrete collection of points, then it should converge to the mean to fp as well. Again, not a proof. For the proof of this, you'd want to use Weierstrass M-test and some other pretty heavy analysis theorems, but yeah, that's the idea. So the reason why we worked with L2, right, because a number of students asked why L2 is kind of a weird collection of functions, yada, yada, yada. The reason why we're working with L2 is because of the synergy here. Given a function in L2, the Fourier series exists because those coefficients are well defined. So I can build the series. And given this, the function, the Fourier series of f converges to the mean. Well, mean convergence is actually a property of L2. That definition used the definition of L2. So the type of convergence that you get for your Fourier series synergizes with this space, right? So if I give you something in f, then the Fourier series converges to the same thing in f. This is a type of closure property called completeness, right? So by working in L2, we dealt with complete spaces, which allowed us to honestly just make Fourier a well-defined topic without having like weird edge points, right? It's kind of like math before you had the ability to take square root of -1, right? There was some like emptiness where like certain theorems don't work. You can't say that every polynomial has a root if you don't have complex roots, that kind of thing. So that's why, like meta-analysis, that's why we did that. Okay. Now, this one is also kind of the least important one for this class. For engineering, L2, yeah, whatever. You mostly care about when things are piecewise C1 and when they're continuous, because that's more physical for ECE type purposes. So if f is piecewise C1, then the Fourier series of f converges pointwise to fp on all x. So if I'm piecewise C1, then I converge pointwise. So that's really nice. But the thing I converge pointwise to is this FP, which might not be F. We've already seen this, right? Over here, I told you that the Fourier series would converge to this picture here, but this picture isn't F, right? Actually, let's apply this theorem. If F is piecewise C1, so here F is piecewise C1. Yeah. Yeah. So since F is piecewise C1, we know the Fourier series converges pointwise to FP. So that theorem's telling me it converges to this. But FP is not F on this interval, right? I moved that point. So you can see the counterexample right there, assuming you trust the theorem. But finally, if F is piecewise C1 and continuous, then it converges uniformly on any finite subinterval. The limit of the uniform limit will always be the pointwise limit, right? So the limit would be this, and here I can't get uniform convergence because discontinuity. That's a deeper math theorem, but yeah, that's the idea. Okay, so TLDR, I always converge in the mean. I always converge pointwise, if I'm piecewise C1, I always converge pointwise to FP, not necessarily to F. And if I'm piecewise C1 and also continuous, then I will converge uniformly to FP on any finite interval, right? So that's what you got, right? Now, if I'm piecewise C1 and continuous, if you go up here to the definition of this, if I'm fully continuous, I don't do any of this. I strictly stick with this, right? And here, for continuity, we're talking about FP being continuous. So since FP is continuous, that means F of A is equal to F, or FP of A is equal to FP of B. That means these match, right? So here I have a completely smooth function. So in this case, I would also converge uniformly to the original function on a subinterval of negative tau over 2 to tau over 2, right? But you don't really need that. Mostly we care about the convergence to FP because that's what we're dealing with at that point. Now, the proof of this is beyond the scope of the class, right? To actually do this, you need to talk pretty deeply about some of the convergence of Fourier stuff. That gets a bit messy. Okay, so engineering application. All functions are piecewise C1 because, yeah, they're nice. I mean, if a function's not piecewise C1, sometimes they're important for like theoretical discussions. If it's like a real world voltage and it's not piecewise C1, something's probably going to break. Not necessarily, but right? So nevertheless, a lot of functions are piecewise C1 in engineering. Typically, engineers can be safe to assume for a lot of scenarios, not all scenarios, obviously, but a lot of scenarios, you can assume things are piecewise C1. Therefore, Fourier series converge pointwise, no space. And if F is continuous, then the maximum error goes to 0. You also get uniform, right? So the idea here is that functions behave very nicely in engineering, so you get this nice piecewise convergence usually, and you can often get uniform convergence, right? But remember, these exist, and these can cause problems over here, right? If your engineering application is assuming this world, but this world is actually what happens for a particular scenario, that can cause things to fail. So keep that in mind. Don't assume the math always maths. Sometimes you actually have to go and dig into the weeds. So here, draw the function that the Fourier series of this converges to, explain the type of convergence, don't compute the Fourier series. Okay, so I'm going to zoom out a tad. There we go. So first thing I need to do is I need to draw this function from negative pi over 2, or negative pi to pi. Okay. So here, if I were to plug in pi, this cancels and gets me a 1. This gets me a 1. This gets me a 1. So at pi, I'm up here at 3. And here, I'll put open circle for now because I don't know what's going to happen at the edge because I need to know what happens here to do that. Now here, if I plug in minus 1, I get 1 minus 1 plus 1. I get 1. So over here at 1 and here. Now, I don't know what happens in the middle. I could go like this. I could have maxima. All kinds of things could happen. But I'm just going to cheat because I already plotted it. Here, what you normally do, take the derivative, find where the vortex is, and then go from there. The vortex is somewhere around here. I don't know exactly where it is, but so I look something like this. If I plug in 0, I will go through the point 1, right? So, yeah, so we'll redraw that. So I'll go here and then through the point 1, Okay, I'm just gonna do that again. You are at 1, you through 1, there we go. That doesn't look like a parabola, but close enough. Okay, so here I'm actually just using the fact that at 0 I go through 1. We know the vortex has to be in the middle. Okay, so here, at this point, it's going to be the average, so it's going to be over here. This point is going to be the average, so it's going to be here. And we'll draw another period. So here I get my pi, the whole length is 2 pi, so I'm going to be up at 3 pi. And I do another d swoop, up, circle, dot below it, right? So that's what the periodic extension would look like. That's what the Fourier series converges to. Now, if I want to describe the convergence, f p is piecewise C1, piecewise, right? But it's not continuous, right? So what this is going to tell me is that I converge in the L2 mean in terms of my pointwise, it will converge to f of p, and uniform is a no-go, right? It doesn't converge uniformly because of these discontinuities, right? There's a theorem, well actually the theorem above says that it doesn't converge uniformly because it's not continuous. Let's just rely on that. So it converges the L2 mean because it always does. Converges pointwise because it's piecewise C1, right? And what it converges pointwise to is always the periodic extension, right? And it doesn't converge uniformly because it's not continuous. So that's the big result. That's the type of thing you need to learn how to identify. This is how this theorem will be applied, right? I'll ask you about convergence. I might draw a picture and say, how does it converge, right? I might give you a function and say, like, determine how it converges. Those types of things are fair game. Okay. So now we're going to talk about Gibbs phenomena. I'm going to pause real. Okay. So for an L2 function with the periodic extension fp, if the periodic extension is not continuous at some point, then the truncated Fourier series will experience growing oscillations at that point. These growing oscillations are called Gibbs phenomena, right? These oscillations don't appear in the infinite sum because I get pointwise convergence. So the idea here is, actually, I'll generate a MATLAB thing real quick. Okay, that is the benefit of having video versions of lectures. So here, I've built a little script, there you go, that shows various approximations of the function x from negative pi to pi using Fourier series. So this is one approximation. As I add more terms, you see I get oscillations. Now here, as I add more terms, notice this peak, right? These spots in the middle, the oscillations kind of smooth it out. And as I add more here, the peak looks like it's not moving. It is moving ever so slightly towards the point pi, and it looks like the peak's not growing, but it is growing ever so slightly towards around 9%. But these kind of waves here smoothen it out. So if I let it run some more, depending on your resolution, you might not see stuff. But if I zoom in here, I get this little growing spike, right? If I add a few more terms, it's running away. Okay, and if I zoom in, it looks very similar to before, right? Here you can kind of start to see that the top's deforming. This is because we're getting to the point where the resolution that I chose to plot isn't enough to capture the frequency of this high frequency wave, right? So there could be some more waves in here that I'm even missing, right? Because this one's not well resolved. This one is, right? Like usually if you have like 5 points, 2, 3, 4, yeah. These ones are well resolved, but this high frequency I'm kind of missing, right? So there could be some more high frequency waves here that are just gone. But this is Gibbs phenomena. it fundamentally occurs near discontinuities. So what's happening is there's a deep theorem in math that says that the uniform limit of a series or sequence of continuous functions is continuous. So the uniform limit has to break, right? And my sine waves are continuous. So what's happening is in order for them to break, build up to make that jump, I need to have really, really high frequencies. And those high frequencies that allow me to make this very quick jump, right? Quick jump, instant in time, if you will, infinite frequency, also lead to this phenomena over here. All right, so it's fundamentally a phenomena of only the truncated series. It does not occur in the infinite series, because the infinite series pointwise converges, no error, well behaved. But it's something that you're going to run into when you try to, if you try to truncate things here, right? Now the problem with this, where it goes even deeper, right? The normal way you would filter this, you go, it's an issue with the high frequencies. So let's just filter the high frequencies. Well, filtering the high frequencies literally corresponds to taking my Fourier series and truncating it, yeah? So you truncate it more, and when you truncate it more, the error in the middle becomes worse, right? I need the high frequencies to make this match, right? So because I need the high frequencies for this to work well, and the high frequencies cause an issue here, you're just stuck with Gibbs. So it's something you need to understand and work with. Now, one thing you can do to get rid of it. We know Gibbs, I've told you, Gibbs is only an issue. Sorry if the saw is loud. But we know Gibbs is only an issue when it's discontinuous. So if I care deeply about the function x, right? Here it's continuous everywhere, but the periodic extension does this thing, right? Where I want to go through 0. What you could instead do is have a little rounding to it. So instead, I smoothen it out with a nice smooth line that connects that way. So instead of dealing with jump I deal with quick round right? That fixes Gibbs, no more Gibbs. And in some contexts, that can be enough, right? So you introduce a little bit of dissipation or something like that, that kind of smooths the edge. But yeah, so that's Gibbs, that's how to handle it. Yep, and now we are officially done with this PDF. I will switch over to the new one. Okay, so the goal of this is to actually give us some more machinery that allows us to more quickly handle some of the Fourier computations. So in general, if I give you a series of functions, so if I give you something where f can be written as an infinite series of these other functions, it's not true that the derivatives match, nor is it true that the integrals match. So I can't freely swap the operations of limits with infinite series. Therefore, I can't freely swap the operations of differentiation nor integration with series, because both differentiation and integration are defined in terms of an infinite series. But it turns out that for Fourier in particular, we can specify when we can do this based off of the behavior of the original function f, just like what we did with convergence, right? So here we're not going to skip over the math of the general form, we're going to jump straight to Fourier. Okay, so if the Fourier series of a piecewise C1 tau periodic L2 function f, that can be termwise integrated to a convergent series. Okay, I'm going to restart. If I give you a function and it's piecewise C1, it's tau periodic, and it's L2, then I always can term by term integrate the series, and the resulting series will uniformly converge, right? So TLDR, if f is piecewise C1 and it's an L2, then I can build FP. Once I build FP, I can build its Fourier series. Well, I can build the Fourier series and FP at the same time. Once I do this, this equation will always be true, right? And the convergence at the end of the day will at least be pointwise. We already know it's going to be uniform, right? We already know that it's going to be, wow, I'm being bad. Let me break, cough. Okay, sorry, got bearings. So I'm just going to redo that whole guy. So 2 parts, right? First one, if I'm piecewise C1 in tau periodic and L2, then once you term by term integrate, you will end up with a convergence series that uniformly converges. If I'm just in L2, I can still integrate, but when I integrate, I'm only guaranteed at least pointwise convergence. So for uniform convergence, I need the piecewise C1, because if this is piecewise C1, once I integrate, it's going to be piecewise C2, which also, since I'm integrating, it will also be continuous, which gives me the bit that I need for uniform convergence. Right here, from just L2, you can always integrate, you can always swap these things. And for Fourier, it will converge, and it will be at least pointwise, but you're not guaranteed uniform. Now here, this you can actually evaluate, right? We know how to evaluate this term, just because it's U substitution with the interval, right? I'm leaving it like this to highlight that you don't know what the initial condition is, right? It's going to take some work to find what that at A does, right? That's because once I integrate, right, I may or may not have a constant term for my Fourier series, and we will actually have to deal with that, right? Now, this directly comes from our previous theorems from the last lecture, right? And then this second comment here is because some of the things might change for constant terms, right? So we have to be a little bit careful with those, but once you integrate it, once you figure out what the initial term is to match it, then you're good. And we'll give an example of doing that. For differentiation, we have more strict requirements. If it's a piecewise C1 tau periodic function, if it's continuous, and it satisfies this property here, namely all these together are really forcing my periodic extension of f to be continuous. So this point plus this point is about the periodic extension of f. If these are met, then f can be pointwise, term by term differentiated, namely differentiate inside here, to give a pointwise convergence series that converges pointwise to the derivative on all values of f where the derivative is well defined, right? So notice if f is piecewise C1, there's spots where the derivative could be L defined because I have gaps, right? So explicitly, if I'm piecewise C1 and it's continuous, then what you can do at that point is just say, if I give you this Fourier series, you can compute this one just by differentiating the terms. And you're guaranteed that the convergence is at least pointwise. Could be better, could be worse, depends on the function. Okay, so the ideas of these are kind of like the when you can theorems. You should know these, right? In particular, you should know the little edge cases. So here I can always do it with integration, but I'm only going to get pointwise if it's L2. But if it is piecewise C1, then I get uniform, which is nice. Here, you can't always differentiate term by term. You need these conditions, so know those conditions. And when you do, you can take its derivative. You're guaranteed pointwise, but not necessarily more. So we are going to end by going through an example of doing this, right? So previously found these two series before. This was a previous lecture where we did these. Use these two series together and the fact that the Fourier series for the pi periodic version, just use these together to go find the pi periodic Fourier transform for x to the third and then x to the fourth. Okay, so that's our goal, right? So first goal, we need to know what x squared is. So if I want to figure out how to get the Fourier series for x squared, what I want to do is notice that the x is a nice function, so I'm guaranteed at least pointwise convergence to this. So here I can, well, just straight up integrate, right? Right, so if I just straight up integrate this series for x2, then I can get one for x3. Right, so here's how that works. So integral of, I need to pick a point. I'm going to pick 0. You can literally pick any point and you will get the result. You'll just have some extra terms to compute potentially. Some of those extra terms could be infinite series. So here, I know x squared is this, so I'm going to write x squared is equal to, and it is equal in the L2 sense, the integral from 0 to x of pi squared over 12 dx plus the integral of 0 to x of the infinite sum, n is equal to 1 to infinity of my minus 1 to the n over n squared cos 2nx. Okay. Now, since my x squared is piecewise C1, and I can integrate term by term, that allows me to swap this order. You can't always swap the order, but you can in this case. Here, if I integrate this, this gets me x cubed over 3. Here, if I integrate this, this gets me pi squared over 12x plus here, sum from n is equal to 1 to infinity, negative 1 to the n over n squared. If I integrate cosine, I get sine 2nx over 2n. Okay. So that's just integrating all throughout, swapping the order. This coefficient does nothing, and I integrate there. Now I have a few problems. This looks just like what I want. I can clean it up to make it look pretty. X is not a Fourier series. So I need to actually replace x. How do I replace x? Well, I gave you what x was. In general, this would be a Fourier series you might need to compute if you're doing these kind of things. Realistically, I would give it to you if I want you to do these type of computations. Pi squared over 12. X is this infinite sum, right? So I'm going to combine these two sums together because they have the same sign terms. So this is going to be sum, n is equal to 1 to infinity, of, this one gives me minus 1, n plus 1 over n, plus this term here. So here, this gets me, if I combine the terms, minus 1 to the n over 2n cubed, all of that times sine 2nx. Okay, so that's what we have there. This is going to be our Fourier series for x cubed over 3, right? So now I want to take this and I want to simplify it just to give me the Fourier series for x itself, or x cubed itself. So I multiply through by 3, and when I do that, the 3 will change my 12 to a 4. So here I can say x cubed is going to be pi squared over 4 times the sum, n is equal to 1 to infinity of negative 1 to the n plus 1 over n. And if you wanted, you could add these two coefficients together, right? Or these two fractions together to make one coefficient. Sine of 2nx. There you go. So that's for x cubed, but we wanted x fourth, right? So the reason why I'm doing x cubed first, this really demonstrates how I handle integrating constant terms. I always have to do the substitution of the x into its Fourier series, right? Now for x to the fourth, I'm going to run into a different problem. So for x to the fourth, I can straight up integrate my x cubed, right? I'm allowed to do that. I'm going to get convergence. Integration's not a problem for Fourier series, right? So I can integrate both sides. It's equal to, over here, this is getting kind of messy to rewrite this, so I'm going to call the whole coefficient Cn. So I'm going to say this whole guy is going to be the integral from 0 to infinity, or sorry, 0 to x of Cn sine 2nx and Cn dx, and Cn will be this guy times that, right? Just for convenience, so I don't have to write the coefficients. Okay, so here, oops, I want the sum. I dropped the sum. Sum n is equal to 1 to infinity. Okay, so here when I integrate this, I'm allowed to swap the order of integration and summation because Fourier series and the convergence, the function's in L2. So here I'm going to get x to the 4 over 4. Ooh, I really hate how this Adobe does this. Anyways, from here I'm going to get the sum. N is equal to 1 to x, or to infinity, of Cn stays the same. My sine of x becomes cosine of 2nx over 2nx. Now, with the negative. Now, the problem here is before, when I had 0, I ended up with sine. Sine of 0 is 0, but cos of 0 is not 0. So I get the other term kicking in, cos of 0 over just 2n, no x, over 2n. Right? So now I have to clean this whole thing up. That becomes kind of the distinction between even and odd here. So this is going to be the sum from n is 1 to infinity of Cn, well, negative Cn over 2n cos 2nx. Here I get plus. Here I end up with just Cn over 2n. Okay, so I have to handle this series somehow. Okay, now that's going to be annoying, as you see. So if I expand this out, I multiply through by my 4, I get x to the 4 is equal to the sum, n is equal to 1 to infinity, minus 4 Cn over 2n. Obviously, I could cancel the 2 and the 4 if I wanted. Cosine of 2nx. And assuming convergence, I'm going to split up these series. Plus here, I'm going to get the sum, n is equal to 1 to infinity, of 4Cn over 2n. And obviously, again, I could cancel. So now I need to actually figure out what this infinite series is. This infinite series is the constant term of the Fourier series, right? All these have cosine. This is the cos of 0. So my options are go take my old Cn over here. It's a telescoping looking series thing, and see if I can actually compute what that series evaluates to, or go compute the coefficient C0 using our old style formulas, our old style way of finding Fourier stuff, to be able to find out what the coefficient is, right? So either you take this nasty expression in the brackets and you find out what it converges to analytically, of which you don't have very many options of how to do that. You haven't done much of that in 119. Or we just say, okay, this whole term is literally C0. C0, we know, is going to be the inner product of x to the 4th with 1. It's also going to, coincidentally, in this case, be equal to n is equal to 1 to infinity of my, I'll go ahead and simplify it, 2Cn over n, right? So this is happenstance, because I know this is the Fourier series, and this is definition. So here I can evaluate this. Here, our interval was defined over a length of pi, so I get 1 over pi, negative pi over 2 to pi over 2, x to the 4th dx. This is straightforward 119 problem. Simplifies to pi to the 4th, 4 over 80. Yep. So once you have this together, that actually gives me the full Fourier series. What I do is I just put these two terms together. So I end up with x to the 4th is constant term. Constant term is pi to the 4th over 80. Plus infinite series, n is 1 to infinity, of I unpack the definition of Cn, and I divide it by 2n, and multiply it by negative 4. So when I do that, I will end up with a pi squared, negative 1 to the n, over by 2n squared, plus 12 minus 1 to the n plus 1, over 4n fourth cosine 2nx. Da-da. Okay, so we'll stop here. The big idea is when I go to integrate these Fourier series, if there is a constant term in the Fourier series when I go to integrate it, integrating will lead it to form up to this x term. Hence, I will need to know the appropriate periodic version of x, that Fourier series, in order to evaluate it. So if I gave you, say, some function that just had a constant, it's some weird function, maybe like sinh or something like that, it's Fourier series. Would that have a constant? Yeah, sinh should have a constant. If that has a constant, then when you integrate that to get your Cauchy series, you end up needing needing to use the appropriate series for x to shift it. Now, the series you use would depend on what domain you chose to expand on. On the other hand, if I have a term like this guy here that had a sine component to its series, when I integrate the sine, I'm going to end up with cosines. The cosine as 0 will give me this leftover infinite series I have to evaluate. To evaluate this infinite series, you could try to do infinite series shenanigans, but half the reason for doing Fouriers is to not do the infinite series shenanigans. So instead, we'll use the inner product theory and find what Fourier would be, or the Fourier coefficient would be in the standard sense. And this actually gets us a way to compute infinite sums, right? Like this thing over here, if I wanted for some reason to compute what this sum was when it was divided by 2n, right? If I found the right Fourier stuff to get it, then I could find the series using that. So it's pretty rich for collecting some of these. It's also like a natural source of getting things like pi to the 4th, pi to the 10th, those kind of things for infinite series. So this is kind of the deliverable for the derivative thing. This is more the theory, true-false questions, right? And then this is kind of the types of things I can ask. I could give you like x to the 4th, use it to compute x to the 3rd. You go take its derivatives, right? And for derivatives, if I were to take the derivative of a Fourier series, this part never goes, like derivative constant goes away, so that's not a problem. Derivative of these terms stay within the set, so that's not a problem. So derivatives, you don't get any of this stuff, but for integration, you do. That's why I highlighted intervals. Okay, so next lecture, we're going to continue talking about some theorems about how things converge, all that good stuff. Yeah, so that is it for today.